Okay, welcome everybody. I hope that it actually worked. I have no idea. So I welcome Arshia Cont from IRCAM in Paris to give our RISE seminar, the first one actually, if it actually works, on Google Hangouts. We will, let me say a few words about Arshia first. He graduated with his PhD from UCSD in 2008. And afterwards joined IRCAM, and IRCAM is actually an institute that works at the intersection of science. And he in particular works on computer music and systems that actually, different kinds of systems, but mostly involved in music. And I believe today we'll hear about something that is actually able to listen, musician play instruments, and then accompany that musician with missing from an orchestra, or anything you want the system to actually play along with it. So there are all kinds of problems, interesting problems involved in that. IRCAM, I said already, is at the intersection of arts and sciences, and maybe I should also say that there's also a collaboration now between Salzburg and IRCAM. We bring in our expertise in real-time and embedded systems, and IRCAM with music background. So I'll hand this over to Arshia.
So, everyone, and thank you for joining in, whether you're remotely connected or physically connected. So today I'm going to talk about our work. So we are in the Mutants team in Paris. So it's a joint between university and the IRCAM Research Center, which is the big national computer research center in Paris, and of course IRCAM. And in our team, we developed a system called Antescofo that is actually being used a lot since about 2 years around the world by artists in general, and I'm going to tell you what it is. So as Chris said, just a few words about our center, IRCAM. So you saw a picture of IRCAM from outside above. So if you come to Paris, we are just next to the Pompidou Center. Okay, so next to the Pompidou Center, you have this fancy fountain, fancy sculptures. So if you're walking there, you're actually walking above our head. Okay? So this is IRCAM. So it was initiated in the late 80s by composer and conductor, famous composer and conductor Piaz, who actually wanted to create a center where artists and scientists collaborate. Okay, so we are a research center like any other research center, but we collaborate mostly with artists, and we do all our research for the arts. So at IRCAM, you have different departments. You have a research and development, you have production department. So we are present in festivals all around the world. We also come from time in the Biennale, which is actually happening right now, and other departments. In overall, we are 180 collaborators in the building with, let's say, 20 to 30 PhD students, artists, researchers. It's not to know that artists are not permanent at IRCAM. The goal is that, so researchers are permanent, artists, they have to circulate. So the projects change all the time. So that's about it. And just in parentheses, so we work for artists, but it doesn't either. So our goal, our main focus is anything related to sound and music. So we have departments who work on hardcore acoustics with partial differential equations. We have people who are, let's say, language people in the computer sciences. We have people who work on learning. We have people who work on signal processing. We work for artistic projects. It doesn't evade us to do industrial transfer. So it's important to know that, so when we present IRCAM, people think that, oh yeah, these are the people who suck public money. But IRCAM is 50% auto-finance, which is very rare, at least in France. So a lot of audio technologies that you see around on your cell phones and stuff like that can be IRCAM licensed. Okay, so a lot of stuff in video games for spatial, etc. Just for your information, since last year, the big Fest concert hall in Salzburg is actually equipped with technology. and I just contacted the person in charge this morning to see what's. Apparently, they're using IRCAM technology for some events for the Easter. So the IRCAM spatialization technology. So let me tell you a motivation of the work in our team. So let's forget about computers. So Mutant team focuses on time programming and the execution of for music. Okay, for a second, let's forget about computers, because people can make music with computers. That's nothing new. So you can always make new sound engines and stuff like that. There is something more interesting happening in musical phenomena, which is when people actually play together. Okay, so this is RDT string with whom we work a lot. So when people play music together, well, I hear 4 musicians, but you can have hundreds of them. Each has his or her own music. So think of them as programs. They are executing them in real time, and they are coordinating their actions together. Okay. The interesting thing is that when you go to listen to a Mozart piece, I can easily use Mozart here since everybody should know about him, since we're in Salzburg for people. So when you go to a concert to hear a Mozart string quartet, you know the piece you're going to listen, right? But every time it's going to be different. That's called an interpretation. Okay, and despite this indeterminacy of the interpretation, there is some determinacy on the result that you're going to obtain. Of course, these computers here, they should be fault tolerant. Okay, so if one of them does an error, you know, the show must go on. It's like, except that nobody's going to die. And so one of our project is to bring this, and so besides this, another amazing thing is expressivity. So if you look at a music notation as a program, it's a rich language actually, because it is defining a lot of stuff happening, and a lot of liberty for environmental interaction and variation. Okay, so the goal of Mutant team is to bring this power to computers. Okay, it's us in that. In a more concrete way, we are interested in bringing the computer in the same equation with musicians. You have computers who have their own music score, if you want, or program. Listen to human musicians, they coordinate their actions, they synchronize their actions, they should be fault tolerant, they should be timely correct, etc. So that's the interpretation aspect that happens in real time. And of course, there is also expressivity, meaning that you need to provide languages that allow people to have at least the same richness, expressivity that they have when they compose music for humans. Okay? Except that when you do stuff with computers, you can do much than playing a simple instrument. You can run different programs that control light, or the programs that can control robots. You can have programs that run real-time transformation on your voice or on the instrument. You can do physicaling. You can do whatever you want. So the computing can be very diverse. Okay, so that's the musical context. The research context, which is the research context, is that we actually do have 2 main activities. The first one here is real-time machine listening. So interaction of the software with the external world is through listening. Okay, so we're not necessarily interested in interaction by pressing a button. So it's artificial perception going on in the machine. It's listening to the musicians through the microphone, and it has to figure out and infer parameters. So this is the machine learning part of work. So keywords are machine learning, Bayesian programming, signal processing, and learning, and stuff like that. I'm not going to talk about that today. Okay? The second part, which is very important, is of course real-time systems. So you have time-synchronous reactive language. You need fault tolerance for during execution. You have dynamic optimization, we're going to see all of that later, and you can do static analysis and formal verification, and of course you have heterogeneous and heterogeneous components. Okay, it's very important that so this is the basis of Antescofo, the software we make. It's very important to know that the relative success of the Antescofo software is not because of neither the machine listening or the real-time system part, because these two components are tightly coupled. Okay, so none of them is useful without the existence of the other. So Antescofo has a lot of composers since 2-3 years of its existence to do complicated with little effort. And we have a very simple slogan: what you see in real time. No more, no less. We try to be deterministic, etc. And basically, you have some sort of a cyber-physical system, if you want, in the sense that you have a program. In your program, you define what you expect in the environment. Okay, it can be the music score that you're going to play, the singer is going to sing, or the pianist is going to play. And then you have another part of your in the same place, which are the reactions to what is going to be heard in the environment. So these are action dynamics. And you have a scheduling machine that is tightly coupled to the listening machine that gets events and also time data to do event triggering and time triggering. And then you have feedback that goes to the stage. Okay? So that's all beautiful, the concrete examples. Okay, so first example is going to be automatic accompaniment. This is our, let's say, great public demonstration. It's very simple. You play an instrument at home, but you have the means to have an orchestra at home, I hope. And you want to play with an orchestra, but you want the orchestra to play at your pace. So this is what we're going to see here. Student at the Paris Conservatory, he's playing this piano concerto by Maurice Ravel with Swiffle, and the orchestra is actually the famous orchestra who is being synced to this performance. Meaning that the placement of the other is So what you need a score that you can find online, and the karaoke that usually you can buy for 90 cents or something like that. You hook it in and it works. So you will see, if you look online, you will see, for example, that we won an industry award years ago, and we invited a singer from the TV program The Voice to come and do karaoke. So she sang Beatles, Hey Jude, etc. So you will find it. It's the same thing. It's the same. So this is our public demonstration. Okay. Now let's get into more complex stuff. So this is a music composition. Okay. So this is a music composition. This is a music written for humans plus computers. Okay. We usually call this live association between the two, mixed music. Okay. So the electronic part, the computer part, is not just something fixed. that you press on a CD and then the musicians are going to play. It's exactly, like that string picture we saw in the beginning. We bring the computer as an intelligent component. It has to listen. So for those of you who can read music, or even if you can't, the top are what the humans are going to play, and the lower parts are going to be patients for the computer, okay? So they correspond to a symbolic representation of the actions that correspond to different, okay? So a program, for example, can be doing some symbolic computing to send you to 16 speakers around the audience. Okay? This is what you're gonna see in the Festspiel if you go to the event during the Easter holidays. It can do physical modeling of instruments, so it can solve differential equations, or it's sound synthesis, or it can do live transformation of the sound of the, so it can be very, very diverse, okay? This is actually how the composer written it symbolically in the score that you can buy in music stores. So what you need to do is some sort of computer language that is going to translate this to machine actions. Machine actions that are going to go to different types of computing with different time criteria, etc., etc. So that's when Antescofo comes in. So this part of the score in Antescofo, so you see that this is the top part is the representation of what the man is going to play, and the lower part are actually parameters that should be sent at that specific point in space and time, I insist, space and to the computer. Okay, so you have discrete actions, you have continuous actions. Some continuous actions, they have to be reactive. Some of them should actually synchronize at the end of a phrase. So you have different types of relationships going on. Some of them are hierarchical, etc., etc. Let's just have a look at a small video that shows an execution of a small part of this. Okay, so it's a piece for violin and live electronics. Okay, so if you know the sound of violin, anything that is not a violin is electronics. Okay. Okay. Okay, as a fade out, don't worry. So let's just have a small look at this, and then we will get into details. So this is the Antescofo score. Actually, the graphics you see here are pure visualization. Antescofo program is text. This is what you see over here. Okay. And currently, the state of the language is that it's a pure control language. Okay? So Antescofo lives in in a host program, which is a real-time environment. In case you're familiar with, there are two very common standards in interactive arts as programs. One of them is Max. Okay? It's actually a real-time graphical, real-time programming environment for audio and video that was made in the 90s. Now it's being commercialized by an American company called 74. And there is also the open source counterpart called the Pure Date. I know that Pure Date is being taught in Salzburg. So Antiscofo actually lives in those environments. What happens is that in those environments, which are basically real-time, but they are timeless, okay? You'll see why. You have programs that show the chain of real-time calculation. Programs that have the chain of real-time calculation. I'm going to go out a second because I know that some people are sending messages just to make sure that nobody's having problems. Nobody's having problems. That's even perfect. So you have implementations of your effect. You can do your effect as you want. Okay, so here, for example, we have some spatialization effects. You have weird sounds, so these are synthesis sounds. You also heard some doubling of the violin, which was basically real-time transformation of the violin. You program as you want. Okay, so what Scofo does is that it tries to organize the controls over time, and each time this place is interpreted live, of course, it's going to be different. So you see that a lot of overlapping of control parameters here. So we have all where things don't overlap. I'm doing it on purpose so that you see how temporal stuff actually overlap. The goal is that each box here can go to a specific effect, which has specific time requirements. And on the lower level and on the higher level, you can have different and various synchronization constraints. Okay, Antis handles that in real time. If the violinist makes a mistake, if he or she changes his speed or tempo, or even if there is a problem. Like so, problems come from musicians. You should never tell them that made a mistake, or it can come from a listening machine because. A real-time listening machine, even the most intelligent one, which is ours, by the way, can make mistakes during real time. You know, you never know what's going to happen. You know, somebody's going to cough, and it goes to the microphone, and he coughs on this note that you're expecting, and nothing should go wrong. Okay, so achieve fault tolerance by the coupling of the listening machine and the real-time system. Okay, so now let's have an overview of the language itself. Okay, so I'm going to skip it. Okay, so as I said earlier, in the Antiscofo language, you have both what's happening in the environment, what is expected from the environment, and also what the computer should do as a reaction. Okay, let's imagine very stupid music score. Even if you can't read music scores, it's very easy to interpret. All circles you see over here, consider them as actions. Okay, actions that have duration. So on the top stack, I have what the human is going to play, and on the left side, I have a very simple and stupid thing, which is what the computer is going to play. So the Antiscofo program for this is first we're going to give the pitches and the durations, physical time, of what might be performed in the environment. Okay, that's it. So we have silence, etc., etc. And then let's look at this. So here you have a phrase which is being repeated twice, and here you have something that's being repeated twice. So said the current state of Antiscofo is pure control. Okay. And the thing we provide, and it's pure message passing. So these are just this message is being sent to receiver play, and the rest is sequencing and compound instructions. Okay, so you have a group. Okay, so we are grouping phrase here. 1/6 corresponds to the delay of the action correspond with regards to the previous action, and then On the lower, you have something that is being repeated at least in one measure twice, okay? So it's a loop. And then we're going to repeat the entire thing twice. So these are, let's say, our discrete actions. It's important to know that the notion of time here. So the delay that I'm noting, number 6, is a musical time. Okay, so for those of you who are familiar with music, music notation is most of the time, or let's say always relevant, in the sense that we give musicians some indication of the speed that they play, but they do as they want. So you have the metronome effect. Huh? You practice with metronome, then you turn it off and you do whatever you want. That it becomes interpretation in the bass. And when you write it like this, it is actually synced to the tempo of the human musician. So we have an intelligence system that detects the tempo of the musician. So they're constantly being scheduled as the musician is playing. But sometimes you might want to have different notions of time. Okay, so you can actually have absolute delays here in millisecond or second. It depends on the nature of the computation at stake. Okay, so let's go to another toy example. So here I'm trying to introduce notion of continuous actions. Okay, so here I'm going to have a very good music score that is being played by a vibraphone. Okay, and the electronic action is just going to be a sinusoid. Okay, which is going to start with the first note, and then gradually and continuously it's going to go up. Okay, sinusoid and changing the frequency. Right? So this is, in our jargon, it's a linear curve. Okay, it's written like this. So it's interesting because if you have the breakpoints, meaning the let's say the discontinuous places of the linear curve, which are actually these 1, 2, 3, 4 points. Okay, I'm giving the breakpoint position in time, in musical time, but the interpolation grain I'm giving actually is in seconds. So I'm sending it every 100 milliseconds to my sinusoid. Okay. Let's do a simulation. So I asked very professional vibraphonists to play this very complicated score. Okay. So let's play this. Let's play this and see what happens, because when you have here, you have a notion of so a musician is never going to play like a machine. They always small deviations. Okay, and you have to know that cognitively speaking, if you trigger an action with more than 20 milliseconds of delay, humans can hear a rhythm. Okay, so the best, your best effort strategy should be less than 20 milliseconds for control. For audio, even if you miss one sample, you're dead. You're gonna hear a click. Okay, let's listen to the sample. So you see the vibraphone is going down. So this is our strategy. So what happened was that, of course, they got triggered together. After that, if you listen carefully, you will see that it's actually slowing down. But it happened in real time. And you cannot have the best prediction. So at each prediction, it should slow down. But they were not synchronous. Okay, so you have. We can give it an attribute. It's waiting. It's interesting because the speed is actually, as we go on, it's going to slow down as well. Let's also simulate. So these are attributes that exist in the entire language. So now let's imagine that the virus is going to skip this note. What should we do? Come on. I always ask this from artists. Now I want to see how embedded system people are going to react to this. What are you going to do? Yeah, of course.
interpolation.
Yeah, but so these have time. What are you going to? Are you going to accelerate or are you going to jump this one? Let's say he's this one. Okay. What are you going to do with this one? Are you going to accelerate or are you going to wait or what are you going to do?
Specify the policy.
That's a good language guy responding. Perfect. Okay. So yeah, so it depends on the nature of the issue at stake, and also musically it can be depending on the philosophy. So if the event is defined as low, it can jump, meaning that you can miss it and it's not important, etc. Or it can have other kinds of strategies so that it will go fast, it will converge, okay? So what I'm trying to show you is reasoning about these things in real time is not easy. So the name of Scofo, the ante of ante Scofo is, so Scofo is score following, okay? The ante, because ante Scofo is an anticipatory system, okay? So the reason that humans can play together is not because they have perfect listening, it's because they anticipate, okay? So they prepare the resource, okay? So if you listen to, I don't know, a complex piece by, I don't know, Beethoven's Great Fugue, okay? You have all these things playing together and you know, nobody can have tight synchrony between them. What is that they say, okay, we're gonna go, but at the end of the phrase, we have to converge, okay? And musicians are very good with saying that, okay, let's start this, and 10 minutes later we finish together. We see that actually in Indian music. In Indian music, you have some raga systems where, you know, the guy starts playing a very complex rhythm, and the second guy, and these are rhythms that do not tie. Okay, so they have some prime relationship. And the guy who's listening and doesn't have mathematical or MATLAB in his head, he knows exactly when to enter, that, you know, 5 or 6 minutes later, they coincide. Okay? They have some anticipatory mechanisms and they have internalized representations. So here, I'm going to show an excerpt from the same piece we heard, where you have a continuous electronic that is going to be easily distinguishable. And the goal is that at the specific point in time, they have to finish their task. They have to be together. So in this case, what's happening is that at each point in time, we are scheduling by anticipating to arrive at a static target in the future. Okay? So it's going to give you like this. That's the electronics. The problem with what we do is that it's just natural. If you imagine the problem at stake, it's very complicated. Because everything is there. It should be smooth. You do not want to have any spontaneities because it's harmful. Okay. So what I'm trying to hear is that let's say that you have a presentation of your score. Okay, on the top you have the human part, on the you have some atomic actions that you're triggering. Okay, what happens actually in real time is that when this thing gets executed, real time is very elastic. So things are not going to happen at the same place, clockwise, if you want. And also, so when you look at a music score, there is Newtonian dynamics between spatial placement and, you know, temporal equations, movement equation, but they totally get decoupled during interpretation, meaning that you have a tempo but the placement of your future event is not based on you. So you have a lot of jittering, or you're starting to slow down. You can't know that in your head you're slowing down. You need to give total freedom to the musician. So the entire question is that we want to give people a language so that they can specify what kind of synchronizing, what is going to happen as much as possible. So for this atomic event, which coincides exactly at the same time as the endless event, it's simple event trigger. It's just alignment with an event. As soon as the machine actually detects that event, the machine listening has a latency of around 5 milliseconds. So this is, let's say, discrete events, but they are hooked to this event. So the trigger of the box, if you want, is event triggered. It's event triggered. But after that, you can, for example, have some sort of a time trigger. Okay, so you hook it, you bind to the tempo of the musician, and as the tempo is going down, it will go down. Okay? It can be scheduled using the tempo of the musician. Okay? So on that line, you have an event whose so it's a dangling event, if you want. It's a floating event for people who do LaTeX. It's a floating event which is hooked to the beginning of this one. So delay with regards to that. So it's also a mixture of event and time triggering, except that every time the event enters here, we have to reschedule the thing. Okay, so this is basically what happens. Because a new tempo is detected, things change. So at the end of the day, the event is going to happen, for example, somewhere here. Okay. Or you have a mixture of these. You can mixture of these, or you have, let's say, a dangling box. You can have hierarchies. And this box by itself has its own clock, whether the musician clock or not. And you can have something that says, okay, you're going to finish, for example, this event, etc., etc. Okay, so these are very basic things. And the funny thing is that it's nothing new or fascinating for composers. Okay, they just do it. You just give them stuff like that, they do it. And keep in mind that these PA write programs. Okay, I'm switching all the time between music score and program. They programs for 150 people. And it's not a joke. They have pieces for big orchestra, and they don't have a simulator at home most of the time. So they can, the language is so powerful. The language is powerful that they can imagine how it's going to get out. And of course, they have a lot of talent. How it's going to be on the stage. They can it in their head and have, let's say, non-faulty authorship. Okay. Just a few words on the synchronization strategies. So as said, you can have different types of missions. So let's say that the white dots you see are the top left box is our ideal program. So the red dots are the events from the environment. Okay. And then in the box you have a continuous and also a discrete event. So for the time being, you have 9 different ways of synchronizing. Okay? And you see that, so what we're doing is that we are altering different events from the environment, and we are showing how it's going to, control is going to go out based on the specification you give. Okay? So you see in some, you have discontinuities. If you use, for example, the tight strategy that you want discontinuities. Okay? Because nobody's going to play the XM tempo exactly as it was written. We're dealing with humans. Or you can have the target strategies. So these are the anticipate strategies that can be either static or dynamic. Okay? So Ravel example, or in the karaoke examples that you can watch online, it's important to know that there is something very subtle happening in the synchronization. If, let's say I'm singing Beatles and he's singing to me and playing back, if I'm listening to the playback and he's listening to me, the result is that we will both slow down. Okay, it's a cognitive feedback. So for that kind of stuff, you need an anti strategy. So it's pushing the musician and at the same time synchronizing with it. It's a very complicated situation. So we've done a lot of tests with musicians to make sure that it's not altering stuff and they do not feel a rhythm, etc., etc. And of course, these are all attributes. Okay, let's make things even worse. Okay, so far you've seen, let's say, anti-score programs that are totally static, even though there is, in the execution, there is some dynamicity going on. You can have scores where everything happens. Okay, so we saw groups and loops, which are phrases and something that is being recorded. We have something used a lot by composers called the whenever. Whenever condition you do this. And we also have processes. You know what processes are. These are dynamic constructions. You can run as many of them. They're similar to processes in most real-time languages. And of course, variables. And the funny thing, there is nothing new. What's interesting in the musical case time. Okay. So by default, what people do is they want their actions to synchronize to the musician. Okay, that's what you see in karaoke. But in some cases, you want the actions synchronized among themselves. Okay, so you can actually define the temporal evolution of a specific process or a specific block based on some variable, for example, being controlled by some other process. Okay? So here, immediately, you're going to have, let's say, buses that have heterogeneous and dynamic time aspects. Okay, so you have two boxes, you want them to synchronize among themselves, but one of them is actually being hooked to a music. So we need to find conflicts. We need to see whether the guy running is not going towards causality conflicts. So that's what we try to do with the formal verifications with Florent Jacques-Marroussier, among other things. And of course, you need to make sure that what you write is going to be true despite all the variations in the environment. So that's also something we can do with static analysis. Even worse, you can have dynamically and hierarchically derived times. Okay? On the right here, you see a small anti-score program. So a program called Trace that is actually plotting a figure. Okay? I'm calling Trace. I'm going to control Trace in a. I'm trying to, so the trace is just a plotting process. So I'm creating a continuous process and I'm trying to plot it. The timing of the process, the first hierarchy, is given by some points in time. Say you start at 60 and then you go to 180 and then to 60 and with 5 music times. And then I give this time as the temporal specification of a group. Okay? And in the group, I'm going to have another continuous process, which is controlling the temporal evolution of another. Okay, so these 3 things are together, they're controlled together, etc., etc. So you can have recursive structures and you can have nested and hierarchical structures. And of course, all this is dynamic. Okay? All this is dynamic. You cannot, you have an ideal way of presenting how it's going to sound, like a music score. Okay? You can play it, simulate it. But in real time, what you want is that all the parallel and concurrent structures, you want everything to come out as you have expected, all the variations. So what I'm trying to say is that music is an interesting case for people who want to study time. So the genesis of musical authorship is that in the music, whether it's contemporary, classical, jazz, or even improvised, you have some organization of material over time. There is no unique grammar, possibly as many grammars as the types of music that exist. You have heterogeneous and heterochronous times. There is no unique musical clock, possibly as many musical times as pieces, okay? You have, for example, notion of spatial time, which means that an event that exists in space doesn't exist over time. Okay? In classical music, it exists, it's called grace notes. Events that exist, but they do not occupy symbolic time, if you want. So you also have continuous time, for example, glissandi on the violin, etc., etc. You have twice invariance despite execution in determinism, so that's called interpretation. And the coordination happens by actions. Okay, so you have multiple components, and you have some potentially non-sense coordination happening among blocks. And of course, this is very important. Musical authorship persists time. Okay? Today, we are performing music that has been written 500 years ago. Okay? Of course, supports have changed, but the language itself has remained invariant to this. This is very important, very, very important. So people make a lot of pieces on Scoffle. We have a lot of concerts. This month we have concerts with Berlin Philharmonic, for example. In a few weeks we go to Barbican Hall, and we are not playing this, so users with me, thank God. So we know it when there are bugs. But we have to also take this feature into account. What is going to be happening 10 years where our computers injured, things are going to. And the real question is, how are we going to articulate dynamically between all these times, both during authorship and also execution? So, not you, but some, let's say, more traditional people are going to say, yeah, you're just going to have a mechanical global clock, and you're going to execute it there. But which mechanical clock am I going to choose? The machine clock, the human clock, the musical clock, the absolute time clock, it's dedicated. So in what I showed you, the way actually it's implemented, given to users, is that we abstract execution from expressivity of the language. All the different timings that you see in complex anti-Scoffle score, they articulate among themselves in a unified form, totally in a dynamic way. And the unifying form is the program itself. So we are doing type checking among different temporal relationships, okay? And we do the best we can. Of course, in implementation, most of the time you need some epsilon clock. But implementation is something that you can abstract implementation from. So far, Scoffle is purely control. It's a message pass host real-time program. But so far I've got propaganda, but we are having a lot of problems because the fact that the language is intuitive for artists makes them program complex pieces which demand a lot of compute, not power, but let's say good utility in terms of, because we don't have, most of the time we don't have computing CPU issues if we just use several computers, but we are having issues with scheduling. Okay? So our host programs or the, let's say, the sense of most multimedia systems, they have static scheduling that like DSP or control or video, in separate chunks. But based on context and dynamically, things can change, and you need to adapt. So we are having a lot of problems. And what we realize is that we have to integrate computing inside our language. So we're dealing with some prototypes where instead of just sending controls to, let's say, an external program, we actually embed C or C++ or other types of DSP code into the program that are, let's say, half legal as modules, and we try to coordinate between them. So we try to integrate programs from elsewhere. So this is why we are interested in working within embedded system design. So the challenges we are facing are integrating heterogeneous programs and assuring time correctness in the same way as doing that in the control domain, but this time doing hardcore calculation on audio, video, or even robotic control. See some videos where we control robots on stage in operas, for example. And of course, transform the way users and designers interact with this kind of programming, because the situation today, believe it or not, is very frustrating, because in all systems, you can make programs that, for example, transform your voice. You know, they're fun, but as soon as you scale to the system, you put 10 together, that's when the system is going to fail and they become unreliable. And usually in concepts, we have at least 50 or 100 of them working together with different properties. And so the inputs of the system can be very different. So we are working on versions of Antistofo that have different kinds of listening. So they can listen to environmental sound, they can get control, etc. And the type of application that you're going to have are going to be very different. So it's going to be a major challenge. And let's see another one.
So let's see, we have questions.
Wow, I think I forgot to share the.
Well, I thought I had at least one student watching us, so
yeah. So we have 2 viewers. Do you have any questions?
3 viewers. Okay, so if you have any local questions, I do have a question. So I was wondering, like you mentioned before the talk actually, you mentioned that these musical systems are actually have stringent real-time requirements to the extent that they're actually even worse than some, safety critical systems for engine control or something, because here the range of error is almost in second range or even below that, right? So if there's any mistake in that, a human ear can have a mistake. Now, can you derive from that potential application beyond music?
From this?
Yes.
So one of the, we are actually working with teams that do not do music. So if you want the bottom line of everything I show you here, which is motivated by, is that you have tasks with different temporal constraints, and we want to put them, some of them are hard, some of them are soft, and the chain of soft can be very varied. One interesting application is robotics. So so we work, for example, with the robotic team in France that make open source, open hardware robot copy. So what these people do is that so it's open hardware like Raspberry Pi or Udo or whatever with Arduino. If you have more money, you put hardcore FPGA inside. What they do is that they code using Python programs. Okay, if your robot is doing one thing, demo for a journalist is fine. Okay? But as soon as you put it in a real complex environment, that's when you need to have different things, different types of middle and higher level controls. What they want from us is that they say, what we want designers to do is that we don't want them to learn all the low level stuff. We want them to write scenarios and, hook them together, organize them over event-based, and, make sure that, ties happen correctly. Okay? So this is a typical example. For example, they're interested in having a music score, but what they're interested in is the whenever construction. Construction hooked, for example, to artificial perception. Because what is the thing with this tight coupling is that, so there is this computer scientist, Peter Van Roy, you know, right, who told us that what is interesting with anti-scuffle is that your users can program with the human concepts instead of mathematical concepts. When you hear the door, a door jam, do this. You know? And the notion of door jam is not very well defined. And you have the same thing with music. You know, so our system is actually plug and play, meaning that the piano thing you saw, it should work on every piano, on every microphone, and in any situation. Because when we are doing a concert in Philharmonic, I cannot ask the 200 people in the orchestra wait for me to calibrate. You know? So we have done a lot of work to make it, you know, plug and play. The flutist has different tuning. Now, I'm not going to tell him, hey, your tuning is 400 instead of 440. So it's also, but the robustness comes from the type of one application is robotics. The other one is that, let me show this thing because I believe it's interesting. I actually saw this, okay, so this is the IEEE as defining, there is a new consortium IEEE called Audio Video Bridging. And so the basic idea is that they're saying that our multimedia systems are not good. They are hooked for audio and video delivery. Okay, meaning that you're on YouTube or Skype, you press play, and you know, you just do delivery of data. It happens more and more, especially in interactive applications, and this is where we come in, is that between the two, between the input and output, you have computations happening. Okay? And these computations, they can vary. Okay? For example, one application of this are cars. In cars, you have more and more of local networks. Okay? So a lot of programs, they talk on local networks, but these networks are synchronous. I mean, the TCP/IP is not synchronous. These guys, a few years back, they said, let's redefine Ethernet. Let's redefine Ethernet and make it synchronous. So took the clock synchronous work by IRCAM at Berkeley. They actually tried to make a series of mistakes and force it to the industry. Okay? So it's called audio video bridging. It's very interesting because you have it on your Apple computers without noise. So everybody's prepared for it to launch. And the idea is that, for example, if you go to concerts, you see that they have all these big gears, 100 cables going out of the big box like this, etc. Everything will disappear. Everybody's going to use Ethernet. The problem with audio is that if you miss one single sample, and you need at least 44,001 samples per second, if you miss one sample, you're going to hear a click and you fire it. It's not you don't have this problem with video. If you miss a frame in a video, I mean, it's not good. Nobody's going to congratulate you, but you know, you're not going to get fired. So these people are defining all these standards. The good news for you is that this standard, 8.1 AS, timing and synchronization for time-sensitive applications with bridge local networks. Last year, they had to take it out. It was published, isn't it? They had to take it out because they could not deal with preemption. They could not. It wasn't good. It wasn't good. It's dealing with traffic scheduling over networks. So they have black boxes. It looks a lot. It's all about what you guys do. You have black boxes. They're leveraging them with some properties, and they do some static analysis to launch the system to see if they meet the delay lines. But dynamically, if one service dies, you know, they have to redo the entire chain and stuff like that, and it's not working. It's not working very well. So that's another main application, and I think it's going to be more and more because, you know, on your cell phones, there's a lot of, so you interact more and more with through concepts with your devices. Okay? For example, in Siri, you can talk to your phone. Okay? So Siri is a little bit like Antescopo with a major difference. In Siri, you have word recognition. You recognize words in the end of the word pronunciation. Antescopo, we recognize it, boom, right away.
Because you already know what.
Because we already have an idea of what's happening. So people can write scenarios and interact with this.
We have to finish. Any more questions?
Short question. What are the constraints on the input audio streams? Do you need one audio input stream per instrument, or do you need multiple instruments?
It depends on the artist. So for some pieces, for orchestral pieces, for example, it depends on what the artist wants. Sometimes we have one microphone that gets the entire orchestra. Sometimes we have 15 or 50.
So it depends on the artist's program.
No, it depends on artist's want.
Okay.
Maybe he wants to do separate thing on each instrument, or he wants to do, and they write a specific Antescopo program for this. So we need the system to be scalable. It's very important. Yeah.
And how about the error tolerance? Because I mean, there is error tolerance, as you told us. But if I, for example, write voice to the microphone, it won't recognize anything meaningful for it. So how big does the error have to be from what it expects from the score to what is actually played?
Okay, so the short answer to this is that the machine listening, so that's my main work, is a probabilistic system. So in probabilistic systems, it's hard to quantify this kind of reason. We try to make it as tolerant as possible, but if you have a backup, at some point it's going to fail. So, up to last year, just to give you an example, before last November, Antescopo was not working very well on piano, because in piano you have something horrible called the pedal. You press the pedal, it's going to make the sound, it has nothing to do with the music score. So we try to make it more, these are probabilistic systems. I personally believe that's a discussion I have from time to time with Flo, my other colleagues at home, that these probabilistic stuff have interest to offer also to people who do hardcore computer science. So maybe you have seen stuff. I know that people do game theory stuff, but those are too basic. Here, we do a lot of branching and with probabilistic reasoning.
We have to wrap up.
If you have any questions, come here or write me an email. Thank you. Should I stop? Yeah. Thank you.